Assalamu alaikum dear students. In previous lecture we discussed the one and ontoness of some functions. Now today we are going to discuss the composition of two functions. But before this, firstly we will discuss this function f of x equals to x upon 2 x minus 2 upon x minus 3, and we will check its bijectivity, that is we will check whether this function is 1 or onto, where the domain is or minus 3 or minus 3 and its codomain is b, which is or minus 1. Because here this function f of x is x minus 2 upon x minus 3, so here it is a rational function. You know that the rational function is defined only when denominator is not equals to 0. So this means that denominator is 0 when x is 3. Hence the domain for this function or this function is defined in or minus 3. Now we have to check this function from f from a to b defined by f of x equals to x minus 2 as 1 or onto function. Now for 1 function, let x1 and x2 belongs to this a, means domain set, which is or minus 3, such that their images are same, that is f of x equals to f of x1 equals to f of x2. Now f of x1 is x1 by this f of x is x minus 2 upon x minus 3. We can define this as x1 minus x2, x1 minus 2 upon x1 minus 3. This also equals to x2 minus 2 upon x2 minus x3, because f of x1 is f of x2 and f of x is defined as x minus 2 upon x minus 3. Now by cross multiplication, after simplifying, we simply get x1 equals to x2. So clearly f of x1 equals to x2 implies that this x1 equals to x2. Hence different elements of a, here this a, have different images in this b, which is r minus 1. So clearly f of x1 equals to f of x2 implies x1 equals to x2. So by definition of injective function, this f is 1 or injective function. Now for onto function. Now let y belongs to b, means it is arbitrary element of this b. So this means that it is a real number except 1. And suppose that f is onto, this means that when we assume that this f is onto, which implies that this element should be in this range set of f, that is there should exist an element in a, means x, such that f of x equals to y. Now f of x is x minus 2 upon x minus 3, that is y. Now here we know y is simply the number except 1, because y belongs to b and it is a fixed number or known number. But we don't know whether this x exists in a and exists or not exists in a. So this means that we need to find x, that is x by cross multiplication is 2 minus 3y upon 1 minus y. Now this 2 minus 3y upon 1 minus y is defined. Now is defined when y is not equals to 1, because when y equals to 1, in this case denominator became 0. When denominator is 0, number is not defined. So this means that this this x is real only when y not equals to 1. So here y belongs to b, because this is arbitrary element of this b, and in this b contains the real numbers except 1, and this x is 2 minus 3y. 2 minus 3y upon 1 minus y is defined when y not equals to 1, but y is not equals to 1. So this means that this x is always a real number, hence a defined number. So this means that there exists for this y, there exists an x which is of the form of 2 minus 3y upon 1 minus y, such that f of x equals to y, or f of 2 minus 3y upon 1 minus y is y. So this means that this y is arbitrary, hence each and every element of b is the image element, so f is onto. Hence in this way this function is bijective. So f is bijective from A, where A is r minus 3, to B, which is r minus 1. Now we will discuss today's topic, which is composition of two functions. Now if we have two functions, f from A to B and g from A to B, so we have two different functions with domain and codomain same sets. Then you know that by the algebra of two functions, we can define the sum function from A to B as f of g, f plus g, difference function as f minus g from A to B. Now the quotient of these two as, and this quotient function is actually this function from the subset of A to B, where A1 is that subset where denominator is not equals to 0, and the multiplication or simple pointwise multiplication function f into g from A to B. So this means that these operations, these four fundamental operations in functions, are defined only when we have two or more than two functions with same domains and with same codomains. Now the situation arises, or now the consider a situation where we have two different functions with different domains. Like if we consider f from A to B and g is another function from B to C, so this means that domain of f is different from domain of g. So we cannot define this sum function, difference function f by g or f into g, that is this f into g is called as the pointwise multiplication. We cannot define this because we can define only these four functions when domain of both the functions is same. So this means that when we cannot define these operations for this condition or in this situation, this means that we have to discuss the new operation, which is called as the composition of two functions. Now here the situation for this composition is, we have two functions f from A to B, g from B to C, that is f is the function from A to B, g is the function from B to C. Here x belongs to A and x is related to y, that is f of x equals to y. Y is element of this B. Now here B is a domain of G, so this means that this y is mapped with Z, that is Z belongs to C and G of y equals to Z, while as f of x equals to y. This means this situation f from A to B and g from A to C is the function, B to C is the function. Now we have to define the composition of these two functions. Now how to define the composition? Let f from A to B and g from B to C be two functions. Then the composition of these two functions, that is f and g, is denoted by g or f means GOF, and is defined as a function from A to C, defined by g or f of x is g of f of x for all x belongs to A. So this means that this composition function, that is g or f, its domain is the domain of f means second function, while as its codomain is the codomain of second function. That is how to define the composition. Now here we have f, a function from A to B. F is a function from A to B. This f maps or relates x with y, that is f of x equals to y. And from B to C we have another function, and this y is related to z by g of y equals to z. Now composition means this GOF is a function from A to C, because by the definition GOF is function from A to C defined by g or f of x is g of x. This GOF, that is g or f, is actually the function from this A to C which relates this x to z with this condition, that is x through f is related with y and this y is related through z. That is this initial condition, x is related with y, this y is related with z through g, but this GOF means that x is related this with z with these two conditions. So this is the composition of two functions with different domains. Now similarly, if we have g from A to B, f from B to C, so this means that then the composition is defined as fog. The fog is function from A to C, which is defined by f or g of x, f of g of x. F of g of x is defined by f of g of x. Here in this second situation, in order to define fog, the domain of second function, meaning g function, should be equals to the range of the first function, that is f. But in here in Goff, domain of second, that is domain of second, which is a, is actually the domain of this function, while as it is codomain is the first codomain of the first function, because codomain of g is c. Here in this situation, in second situation, or in order to define fog, the domain of this is g of g, while as its codomain is c. In this way you can define fog and Goff. So inshallah, in tomorrow's next lecture we will discuss the examples, or we will do some problems on composition of two functions. So thank you.